And because we are quite a bit late, can I ask you to deliver the second lecture immediately,
yes.
if it's not a problem for you?
No.
Okay, great. Thank you very much.
Where I have to find it.
The second lecture is
Yes.
hydropower development and environmental impacts for our audience.
I hope you can see, huh? It's okay.
We can see it's okay.
Yes. So I have, I don't want to take too much time from the others. Now, hydropower development and environmental impacts. I've taken two case studies, a large hydropower scheme in an alluvial valley, a small diversion type scheme upstream somewhere in the mountain range. Structure, classification of impacts, case studies, methodology for assessment, summary, and conclusions. So main objective is identification and assessment of environmental impacts and strategies to achieve a compromise among socio-economic and environmental goals. Hydropower plays a very essential role in my country. We have about 60% of total renewable energy originating from hydropower. So it's really important for us. We have no nuclear power station in operation, and it's considered as a renewable, non-polluting way of power generation, but you have nothing for free. So it has some severe adverse environmental impacts. And this is the global installed capacity. So mostly this, the red, purple red refers to China. This is Brazil, United States, and somewhere here is Austria. And this is the situation of hydropower schemes in Austria. So each dot refers to a scheme. In total, nobody really knows, but I think we have more than 4,000 hydropower schemes in Austria, from which maybe 3,800 are really very small schemes, but they are somewhere included in the list. And these larger symbols here in the map refer either to reservoirs or to large hydropower schemes. And you see most of them are located in the mountain area to the left, and some of them are located along the Danube here to the right. The others are medium-sized. We have impacts which are dependent on the type of hydropower, then where they are located, and on the technical layout. Also, the impacts are dependent on the way how the hydropower schemes are operated. So even this would be a presentation for its own. I only say it's not only the scheme, you have to consider more to assess the impacts. So they change the runoff pattern. They might reduce floods. They heavily modify the sediment regime, and they modify local climate. And the largest impacts are on the terrestrial and aquatic ecosystem. Here, these red symbols here indicate a large reservoir, and this reservoir in the mountains, you see it here, changes the seasonal pattern. So the natural flow is heavily modified because these reservoirs store the water in springtime, fill up the reservoir and release it later on. So you see here the natural flow conditions and the operated flow conditions. Seasonal pattern has been changed. This is the hydropower utilization along the Danube. So it's not anymore a free-flowing river. it's a series of reservoirs, one after the other. Only this scheme has been abandoned because of environmental concerns, which were really leading to conflict among our government and eco activists. I would like to speak about this hydropower station here. So it's a run-of-river scheme in an alluvial floodplain. And you see, this is the Danube here to the right side. And what you can see previously, I tell you, you don't see it too much. Previously, this main river was connected directly to all the tributaries, and there are many, because the impounded section is about 25 kilometers long. Now, the tributaries had to be diverted downstream on both sides, and the connection with the floodplain has been disrupted. So, mostly the hydropower scheme modified the morphometry of the cross-section of the river. And this had impacts on fish population, on water birds, on macrophytes, etc. Previously, we had a strong interaction also in the groundwater system between the main river and the corresponding groundwater regime. Now they are separated by an impoundment, and to avoid seepage to the groundwater, which would raise tremendously the groundwater table here, they are completely sealed from each other. This was the situation prior. This is the situation today. So heavily engineered in cross-section, etc. Previously, we had tributaries, we had islands disappeared. And all these has impacts on, for instance, fish population, water birds. A lot of sediments are trapped in the upstream part. Silt is trapped close to the weir, and you cannot dredge. The only option you have is to dredge it, but you cannot release it downstream, for instance, during floods. There's a technical problem, no time, but it's more or less, it's impossible to do so. We monitored, here you see the recent flow velocity, and here, no, sorry, that's wrong, that's wrong. Here you see the water table as it is now. This thin line, this is the water table as it was. As a consequence, here we had the flow velocity. It's more or less the same before construction, so around 2 meters. Due to the hydropower scheme, it's heavily modified in its flow velocity, going down to about 0.2 meters per second and even less. And this creates sedimentation, and this changes. Here you see the rheophilic fish species in by the black bars, and these are the eurytope fish species, so those who are used to live in an environment with low flow velocity. And you see, there are differences wherever you go. The rheophilic species in the upstream part are still found. When you go to the middle of the impoundment, so somewhere here, then you see they drastically were reduced. And the typical fish, I don't know their name, I'm not a biologist, they became more and more. So the biology has been completely changed. Groundwater and vegetation cover. Groundwater table was previously heavily fluctuating, as you can see. Then the hydropower scheme was put into operation, was here. It was more or less stable, like a bathing tube. Again, we applied a systems model, and we could show this is the difference in groundwater table before and after implementation. So here, the green areas are somehow better. The yellow and brown areas indicate a decrease in the groundwater table, means major parts of the floodplain started to dry out. We measured the biological productivity at the wet site and at dry sites at several locations, and it turned out that the dry sites have a much longer productivity, and this also has impacts on soil formation, etc. Also, the input of nutrient-rich sediments, which was prior to the construction often the case during flood events, stopped more or less for the whole period. Only sometimes floods are still released to the hinterland. Conclusion: management regime is a difficult task, and under the given settings, it cannot be really solved. And this generates problems even 50 kilometers downstream, because after the last hydropower station, we don't have enough sediment transported from upstream by the river. What happens? We observe river degradation. Degradation rate is about 3 to 4 centimeters a year. But think about, in 10 years, it's 30 to 40 centimeters. In 20 years, it's about 1 meter. So the whole floodplain starts to dry out. And this means the vegetation typical for floodplains is disappearing. I think I have to close here. I've also an example of a small hydropower scheme, maybe I say in general a few words. We have, as you could conclude from the previous maps, at least 3,500 small hydropower schemes. Small in this case means below 5 megawatt. And they contribute also, it's an uncertain figure, 4 to 6% of total hydropower generation. Many of these schemes are privately owned. And now the discussion starts sometimes, well, smaller schemes are probably better than large schemes. Small is beautiful. I'm hesitating about. I don't think so. The only benefit I see is that it's easier possible to remove them. If you buy the hydropower scheme from the private owner, then the public could do what they want. But small schemes have, of course, smaller impacts. But when you have 3,000 small schemes and you sum up, you have also very severe impacts. And the problems I've previously described with respect to a large scheme is here even more relevant. So sediment management, it's more or less really unsolved. There are some measures when you construct a new hydropower scheme you can think about, but it's rather difficult. Then each hydropower station is interrupting the river continuum. Now it's legally binding that fish ladders are being implemented, and it has been done in many, many cases, but not everywhere. And this means fish cannot migrate upstream. This is only an example what should be considered, and here I will stop. This is a typical example. This is a river course. Then somewhere a weir is being built, and the water is abstracted from the river via an artificial channel on the left side, and not too much remains in the old riverbed on the right side. More or less, the riverbed dries out because the operators of the hydropower scheme, they have long-lasting water rights. Some of them are forever, and this means they can rely on their water right that they have to release only a small amount of discharge to the old river section. And therefore, considering that we have thousands of these schemes, we should be very concerned about the impacts of hydropower. So, summarizing, hydropower plays an essential role in carbon-reduced energy supply strategies. It's very essential, but we change our environment substantially. Seasonally, in short term, in long term, we change the sediment regime, and we have losses, we observe losses in habitats, especially wetlands, and due to engineering works in natural river systems. Some of these stations may reduce the flood probability when this depends on the operation and on the structure. A run-of-river scheme, as I've presented, does not reduce the flood probability at all, only at a local scale. But when you combine it with water storage, an upstream reservoir somewhere in the mountains, this may help to reduce a flood probability in the headwaters. And it's possible theoretically to find a compromise solution among environmental impacts and hydropower generation. And this is what you see here. We tried to assess the economic efficiency. It's a real case from a hydropower scheme. And we tried to assess the environmental quality by considering water quality in the river, impacts on the habitats, etc. And each point here would refer to one possible capacity when you build a hydropower scheme there. So if you don't build any hydropower, then, if you don't build any hydropower, the environmental quality would not be changed. But, so it would be one. But you wouldn't produce any electricity. The economic efficiency would be zero. When you take out the whole water from the river, well, you would have the highest theoretical economic efficiency, but the environmental quality would be poor. The river would dry out and no biology as it was would develop anymore. So if I would dream, maybe before Christmas, I would say this would be an ideal point. Maximize economic efficiency and maximize environmental quality. But it would be a dream. One theoretical way how to analyze the problem would be, let's look for alternatives, capacity of the scheme, which are as close as possible to this ideal point. And this would be somewhere in the range between 1.8 and 2 cubic meters per second, if we follow that. But again, we would need carefully to discuss how we assess it and what we measure, etc. That's only a small part. Thank you very much for your listening, okay, and that I took your time.
Thank you, Professor, very much for this important and most of all useful lecture. As a citizen of Bosnia and Herzegovina, I know what are the problems of the Danube River Basin, especially with pollution, which is not important in my country, unfortunately. That is the thing we don't take care as we should. And that is the problem when we are just a neighbor of Europe, not a part. And so we don't have obligation to fulfill our duties. So thanks again. And I have to follow my schedule and to announce our next lecturer.
May I say one sentence only?
Yes,
of course. I would like to thank you, but don't consider that as being unpolite. But as I said, I'm now in Odessa, not in my home country, and they have scheduled at 5 o'clock a meeting, and I have to leave our group now. So I apologize for that. Yes? Thank you very much.
Thank you very much, Professor.